Blockchain is a decentralized, distributed ledger technology that securely records transactions across multiple computers. Think of it as a digital record book shared by many, making it tamper-proof and transparent. Traditional systems like banks rely on centralization, where one entity maintains and controls all records. This creates a single point of failure and potential vulnerability. In contrast, blockchain employs decentralization. Instead of one central authority, data is distributed across a network of independent computers known as nodes. Each node maintains a copy of the ledger, connected in a peer-to-peer network. This distributed approach ensures no single point of control. By removing central control, blockchain enhances security through redundancy and resilience against attacks or failures. Data in blockchain is organized into blocks. Each block contains transaction information, a timestamp, and a unique fingerprint called a hash. The hash acts as a unique identifier for each block, created from the block's data. This hash links the block to the previous one, forming an unbreakable chain. As shown in this diagram, blocks are connected through their hashes, creating a secure, chronological chain of data. In this broader view, you can see how blocks are distributed across the network, with each node validating and storing the chain. Hashing is a fundamental concept in blockchain technology. It uses cryptographic algorithms like SHA-256 to transform block data into a unique, fixed-size code called a hash. As shown in this diagram, plain text input is processed through the SHA-256 algorithm, producing a consistent hash output. This process is deterministic, meaning the same input always generates the same hash. The hashing function takes plain text and converts it into hashed text, which appears as a random string of characters. This transformation is one-way and irreversible. If even a single character in the block's data is changed, the entire hash value changes completely. This property makes tampering with blockchain data easily detectable. In blockchain, each block includes the hash of the previous block, creating an immutable chain. If someone tries to alter data in an earlier block, all subsequent hashes must change, which requires immense computational power and is practically impossible. Blockchain relies on public key cryptography to secure all transactions. Each participant has two mathematically linked keys: a public address visible to everyone, like an account number for receiving funds, and a private key kept secret, acting like a password for authorizing transactions. The public key can be shared openly for encryption, while the private key is used for decryption and signing. This asymmetric system ensures that only the owner can access their funds or prove transaction validity. Here's how it works in practice. A message or transaction is encrypted using the recipient's public key, creating ciphertext that only their private key can decrypt. This ensures secure communication and transaction integrity. When sending a transaction, you sign it with your private key. This creates a digital signature that proves you authorized the transaction without exposing your private key to the network. The signature uses cryptographic hashing to ensure the transaction hasn't been tampered with. This cryptographic system provides secure, verifiable, and relatively anonymous ownership of blockchain assets. Transactions are authenticated without revealing sensitive information, enabling trustless peer-to-peer exchanges. In decentralized blockchain networks, transactions need validation without a central authority. Consensus mechanisms achieve this. Two main types are proof of work and proof of stake. Proof of work requires validators to solve complex computational puzzles. The first to solve gets to add a new block and receive a reward. This method uses significant energy. Proof of stake works differently. Validators stake their cryptocurrency as collateral to participate. The more they stake, the higher their chance of being randomly selected to validate transactions and add new blocks. If successful, they earn network fees. If they act maliciously, they lose their stake. In proof of stake, validators are chosen based on the amount of cryptocurrency they hold and are willing to stake as collateral. This approach selects participants proportionally to their stake, ensuring security through financial commitment rather than computational power. Unlike proof of work, which requires intensive mining, proof of stake operates by locking up cryptocurrency as stake. Validators earn rewards for validating blocks, but face penalties for dishonest behavior, making the system energy efficient and sustainable. The The staking process involves selecting coins, choosing a staking wallet, and locking tokens to participate in validation. This creates a secure network where the probability of being chosen depends on stake amount, promoting fair and low-energy consensus. Overall, proof of stake provides an efficient alternative to traditional mining, supporting the growth of sustainable blockchain technology. When a transaction occurs on a blockchain network, it begins with the sender initiating the transfer. This could be sending cryptocurrency, executing a smart contract, or any digital asset exchange. The transaction details include the sender's address, recipient's address, amount, and a digital signature for security. Once initiated, the transaction is broadcast to the entire blockchain network. This decentralized approach ensures that multiple nodes across the network receive and can validate the transactions simultaneously, preventing any single point of failure. Validators on the network, which could be miners in proof-of-work systems or stakers in proof-of-stake systems, now check the transaction's validity. First, they verify that the sender has sufficient funds in their account to complete the transaction. This prevents overspending and maintains the integrity of the blockchain's ledger. Next, validators verify the digital signature using cryptographic methods. The signature proves the transaction was authorized by the sender and hasn't been tampered with. This involves hashing the transaction data and checking it against the signature using the sender's public key. If all validation checks pass, sufficient funds and valid signature, the transaction is approved by the network validators. This consensus ensures that only legitimate transactions proceed through the system. Approved transactions are then grouped together and added to a new block. This block will be linked to the previous block in the chain, maintaining the blockchain's chronological and immutable record of all transactions. The block creation process involves additional consensus mechanisms to finalize and secure the block. Once a block is filled with validated transactions, a validator proposes adding it to the chain. Other validators verify the block's contents and the hash. If a consensus is reached, the block is added to the chain. The block becomes permanent, adding to the immutable chain. Smart contracts are self-executing agreements written in code and stored on the blockchain. They automatically enforce the terms of a contract when predefined conditions are met, without needing intermediaries. Unlike traditional contracts that require lawyers or courts to enforce terms, smart contracts run automatically when their coded conditions are satisfied. The code is stored on the blockchain, making it transparent and immutable. Once deployed, the contract executes based on real-world data or user inputs. When predefined conditions are met, the contract triggers automatically. For example, if a payment is received, the contract might release funds or transfer assets. This eliminates the need for intermediaries, reduces costs, and ensures trustless execution where parties can rely on code rather than human judgment. Tokens are digital representations of assets on a blockchain. They allow real-world or virtual items to be stored, transferred, and managed securely on the network. Fungible tokens are interchangeable and identical in value. They can be traded one for one, just like traditional currencies. This makes them perfect for cryptocurrencies, where each unit represents the same value and can be divided into smaller parts. Non-fungible tokens, or NFTs, are unique digital assets that cannot be replaced by another identical item. Each NFT has distinct properties, making them ideal for representing one-of-a-kind items like digital artwork, collectibles, or even real-world assets like property deeds. Tokens enable programmable money through smart contracts. These self-executing agreements can automatically transfer tokens based on predefined conditions, eliminating intermediaries and enabling complex financial transactions like conditional payments or automated royalties. Tokens create new forms of digital ownership by tokenizing real-world assets. This process breaks down valuable items into tradable tokens, enabling fractional ownership and democratizing access to investments in everything from real estate to artwork. In summary, tokens represent assets on blockchain in flexible ways, from interchangeable cryptocurrencies to unique digital collectibles, enabling programmable money and revolutionary ownership models. Layer 1 refers to the base blockchain network, such as Bitcoin or Ethereum. This is the fundamental layer that handles all core transactions, maintains the ledger, and provides security through its consensus mechanism. Layer 1 solutions process transactions directly on the main blockchain, which can lead to higher fees and slower processing times during network congestion. Any changes to Layer 1, like protocol upgrades, affect the entire network and require consensus from all participants. Layer 2 solutions are built on top of Layer 1 blockchains to improve performance. They handle transactions off-chain, meaning outside the main blockchain, which significantly reduces fees and increases transaction speed. Examples of Layer 2 solutions include the Lightning Network for Bitcoin, which enables instant micropayments, and Polygon for Ethereum, which processes thousands of transactions per second while settling final results on the main chain. The key difference is that Layer 1 focuses on security and decentralization at the base level, while Layer 2 optimizes for scalability and efficiency. Together, they create a more robust and usable blockchain ecosystem. In 2023, Ethereum fully transitioned to proof of stake, significantly reducing its energy consumption and enabling more transactions. This was a major milestone for sustainable blockchain technology. Different blockchains operate in isolation, creating silos that prevent communication and asset transfers between them. Cross-chain bridges solve this problem by connecting different blockchains, allowing them to communicate and transfer assets seamlessly. Polkadot uses parachains connected to a central relay chain to enable interoperability. This allows secure communication between different blockchains. Other solutions include Cosmos, OneChain, and Chainlink, each offering unique approaches to bridging blockchains. By breaking down silos, cross-chain bridges create a more interconnected ecosystem, enabling seamless asset transfers and improved scalability across the blockchain landscape. Many countries are exploring or launching central bank digital currencies, or CBDCs, which are digital versions of their national currency. These currencies use blockchain technology to enhance the efficiency and security of payments. CBDCs can be implemented through different architectures. Direct CBDCs involve direct claims on the central bank. Hybrid architectures use intermediaries onboarded by the central bank. Indirect CBDCs involve claims on intermediaries fully backed at the central bank. Examples include China's digital yuan, which processes over 500 million daily transactions, and the Bahamas Sand Dollar, which enables programmable payments. Quantum computers pose a significant threat to blockchain security. These powerful machines can break current cryptographic algorithms like RSA and elliptic curve cryptography that secure blockchain transactions. Quantum computers use qubits arranged in a quantum substrate, operating at extremely low temperatures to maintain quantum states. This allows them to perform calculations far beyond classical computers. Elliptic curve cryptography relies on the difficulty of solving discrete logarithm problems on elliptic curves. Quantum algorithms like Shor's algorithm can solve these in polynomial time, breaking